The Earth's core is slowing down, the science that terrifies geologists. The day ticked long by a hair, just a fraction, and somewhere over the South Atlantic, satellite electronics crackled as compasses in northern cities drifted by a sliver, as if the planet itself was breathing wrong. Weeks later, a sleeping 9-class fault started creaking again. Separate weirdness or the same whisper from 3,000 miles down? If the planet's engine is stalling, the magnetic shielding we count on gets patchy. Power grids get touchy. Airlines reroute. GPS timing, finance's backbone, goes jittery. Here's the part that rattled geologists. The inner core has slowed relative to the surface. For the first time in about 4 decades, the planet's heart is offbeat. To understand why the planet's engine is bogging down and why that touches your flights, your grid, and your phone's map, we need to go back. And inside. Roadmap. The plot. We're unraveling. We're going to unravel this like a mystery with receipts. First, the clock no one can argue with, Earth itself, hiccuped. Not in hours or minutes, but in millisecond nicks and bumps that high-precision timing labs live and die by. Then, the magnetic field started acting moody. The South Atlantic anomaly widening, the North Magnetic Pole hustling towards Siberia, regional weakening that makes satellites sweat. Meanwhile, deep faults began showing patterns that don't look like dice rolls. These aren't jump scares. They're chapters of the same story, and they translate into detours, downtime, and dollar signs right now. Here's the promise. We'll show how tiny rotational changes point to energy trades between the core and the mantle, how liquid metal flow reorganizes when the inner engine stutters, and how that stress migrates up into stone. Along the way, we'll open the drawer with hard evidence. Changes in the length of day, field maps from satellites, repeating earthquakes that double as tomography, and odd clusters in seismic history. We're not guessing, we're following the breadcrumbs. The plot twist is who noticed first. Military-grade timing systems and financial exchanges, tuned to billionths of a second, flagged anomalies before geologists did. When you settle trades or steer a missile, 1/10 of a millisecond matters. That sensitivity quietly logged Earth's tiny rotational swings, and those logs became the first clue that something deep was giving up, or taking, angular momentum. We'll climb an evidence ladder. Step 1, rotation data. We'll hit the leap second drama, why there's talk of negative leap seconds, and what changed around 2008 to 2010 when seismic doublets revealed the inner core's slowdown relative to the mantle. Step 2, magnetic records. We'll lay out the South Atlantic anomaly's growth and the pole's sprint, and what that says about the outer core's convective plumbing. Step 3, seismic clustering. Not prophecy, not doom charts, but real periods when big earthquakes grouped more tightly, and why even tiny torque changes can modulate already loaded faults. Step 4, climate feedbacks. Ice moves, ocean slosh, mass shifts, and that nudges rotation too, stacking with what the core is doing. Small numbers, long timelines, real consequences you'll feel in grids, flights, and finance. Who has skin in this game? Cities at high latitudes where storms and field gradients hit harder. Grid operators managing transformers that don't like geomagnetically induced currents. Airlines flying polar routes, watching radiation meters, and rerouting at cost. Farmers relying on precise GNSS for planting. Everyone whose money moves on a timestamp. And yes, your phone's map app leans on the same fragile chain. Today, not someday. Why spend an hour here? Because the story was split into silos. Rotational dynamics sat with geodesists. Magnetism lived with space physicists. Seismology guarded the core. Climate kept mass redistribution to itself. Each field had a page. Together, they make a novel with foreshadowing and consequences. Our job is to stitch them into one narrative. You can feel in your bones when an aurora wanders south or a grid operator asks for a transformer spare. Now, guardrails. We'll stay inside, verified facts. The 2024 Nature paper made the slowdown case with repeating earthquakes across 3 decades. Day-length impacts are thousandths of a second, not minutes. Magnetic weirdness like the South Atlantic anomaly is real and monitored, not doomsday hype, where scientists argue correlation versus causation in quake clustering. We'll say so. And when this touches you, rerouted flights, GPS, hiccups, transformer alarms, we'll flag it. Here's how we'll move. We cold opened at the crest of the wave. To see what lifted it, we start with the planet's clock. the length-of-day quirks that timing labs caught while geophysicists squinted. Then we watched the magnetic shield's mood swings, the messenger that broadcast the core state. After that, we walk fault lines to see whether earthquakes don't. Roll dice with honest limits. We'll pull back the curtain on the handshake at 2,900 kilometers. Core-Mantle, coupling that moves momentum uphill. We'll step into the furnace to ask why the core would slow. Inner core growth, heat, composition, and changing boundary conditions. Then we come back up for surface telltales. You can actually notice now. Aurora shifts, satellite anomalies, compass drift, gravity fingerprints. From there, we map the fallout. Grids, GPS, flights, finance, places where invisible millisecond nudges and shifting field lines hit wallets and schedules. We run the Megathrust math. Who hurts first if stress tips? We bring in ice and water, because climate is already leaning on the same levers. We read the long memory and paleo records to see if past weak field intervals echoed with trouble. We close with the playbook, monitoring, hardening, and honest uncertainty, and a 10-year dashboard you can screenshot and track. First clue came from the one clock you can't argue with, Earth itself. If you care about flights arriving, trades clearing, or your map app staying sane, this is where the cascade starts. Clue 1. The planet's clock went weird. The first hint wasn't a bang, it was a whisper in decimal places. Timing labs saw Earth's day length nudge by thousandths of a second. Barely there, unless your job is keeping the world in sync. Here's why that matters. Everything stacked on precise time. Navigation, stock trades, satellite handshakes assumes the planet keeps steady time. When it doesn't, humans improvise. Start with a simple idea. The length of day isn't fixed. The oceans slosh, winds shove, ice ships wait, and Earth politely speeds up or slows down by a hair. Meteorologists track this using atomic clocks and a global network that compares Earth's spin to a time standard. Most days, the correction is tiny. But recently, the pattern broke just enough to make nervous people take notes. In the background was a brewing debate about leap seconds, the awkward adjustment we sometimes add to keep civil time matched to Earth's rotation. For years, folks worried we'd soon need negative leap seconds because Earth briefly spun faster than expected. The headlines made it sound dramatic. Inside timing labs, it was spreadsheets, size, and calls to satellite operators. If we tweak time, will your fleet stay in formation? For you, that means navigation, ATMs, and cell towers depending on a planet that suddenly isn't keeping perfect time. Now remember the promise we made. We're following breadcrumbs. Around 2008 to 2010, a different signal slid into view. Seismologists studying repeating earthquakes found that the inner core had slowed relative to the mantle. The data came from doublets, quakes in the same place with the same mechanism, years apart. Their seismic waveforms shift if the waves pass through a changed interior. And they did. A 2024 Nature paper tightened the case. 121 near twins from the South Sandwich Islands crossing the inner core showed that the solid center wasn't outracing the surface anymore. It was backtracking ever so slightly, tiny, invisible, and yet cascading into decisions in control rooms you never see. So what do clocks have to do with that? Earth is a system with shared angular momentum. If one part exchanges speed with another, the planet's surface rotation can tick faster or slower by milliseconds. Timing networks, those quiet watchers, saw small but persistent departures, the kind that don't line up cleanly with just atmospheric winds or El Niño. That doesn't prove the core did it alone, but it fits a picture where internal torques are in the room. Meanwhile, a micro story from a place that rarely gets stories. A national timing center prepped software for a possible negative leap second, while a geophysicist down the hall reprocessed seismic rays cutting the inner core. The two teams barely talked. Same building, same planet, different languages. When the nature result dropped, someone finally walked over and said, "This might be the shove you're seeing." Translation. An invisible change 3,000 miles down was about to change how their servers kept the world on time. To understand the shove, we need a bit of physics without the headaches. At the bottom of the mantle sits a rugged boundary, and below it, a conducting ocean of liquid iron, the outer core. The solid inner core sits inside that ocean like a heavy, slightly offset gyroscope. The outer core's flow drags on the inner core electromagnetically, while bumps and topography at the boundary let the mantle and core exchange torque. Think of a figure skater whose arms are the mantle and whose torso is the core. Pull in, push out, the overall spin and posture adjust. Nobody's doing backflips here, just millisecond nudges accumulated over years. Here's the rub. The signals are small and messy. Winds push harder than the core by the day, Yet over decades, that persistent internal torque shows up. The slowdown that started around 2008 to 2010 means the inner core now lags the mantle a touch. The immediate surface effect is tiny. Vidale called it almost lost in the noise. But the pattern matters because it tells us energy is moving inside the planet's engine. Paradox. A millisecond you can't feel decides whether planes detour and grids run hot. Every 30 seconds, ask if you'd keep watching. So here's a detail. A stock exchange's time server flagged a rash of micro-jitter during a solar storm run. Engineers blamed space weather first. Later, analysts noticed the baseline drift had been present for months, independent of the storm. It lined up with subtle length of day changes. Did the inner core cause their headache? Nobody can sign that affidavit. But planners started treating Earth's rotation like a variable, not a constant. While the clocks ticked funny, a debate got loud. Are we correlating noise with noise? Scientists push back hard, and they're right to. You can't declare causation with a millisecond and a model, so the community built an evidence stack that turns invisible shivers into actionable risk. Remove the winds using atmospheric reanalysis. Strip the oceans using ocean angular momentum models. What's left includes glacial water shifts, groundwater pumping, and yes, interior torques. That residual still breathes with the decades. There's one more breadcrumb. Normal modes, planet scale ringing after big quakes, also hint at inner dynamics consistent with a rotating, slightly anisotropic inner core whose rate varies. Different methods, same sign. When independent tools hum the same tune, you listen. So this is the moment everything changed for our story. Not because the day got longer by a blink, but because the blink had a fingerprint. The timing anomalies, the leap-second jitters, and the seismic doublets all point downward. The planet's clock went weird, and the weirdness had a direction, from the core outward. While those numbers accumulated in back rooms, something else began to speak louder, in color and sky glow. Magnetism is the messenger, but the muscle shows up as stress in stone, and the messenger had things to say. Clue 2, the magnetic shield's mood swings. While the clocks whispered, the sky flickered. Pilots flying over the South Atlantic started logging odd instrument resets at the same altitudes, same longitudes. If you've flown those routes, your itinerary is now partly written by molten iron you'll never see. Satellites crossing a familiar corridor saw their computers flip into safe mode more often. The maps gave it a name decades ago, the South Atlantic Anomaly, but the shape has been changing, widening, splitting like a bruise that refuses to heal. That matters because Earth's magnetic field isn't just a pretty aurora machine, it's a radiation bouncer. Where it thins, the line gets long and rowdy. Start with stakes. You ride this shield every time a GPS chip triangulates, every time a power grid hums under a solar storm, every time an aircraft takes a polar shortcut. A weaker field means high-energy particles punch deeper toward us. For satellites, that's bit flips, degraded sensors, and shortened lifetimes. For airlines, it's higher radiation doses on certain routes and the occasional detour that burns fuel in minutes. For pigeons, turtles, and whales, it's a compass that's a little less trustworthy. Nobody panics when the aurora dances. They panic when the lights on the ground go out. So, what actually happened? The North Magnetic Pole sped up its sprint from Canada towards Siberia over the last 2 decades. Enough that navigation models needed mid-cycle updates. Field maps from dedicated satellites, Orsted, Champ, Swarm, show regional weakening over South America and Southern Africa, while the anomaly under the South Atlantic expanded and in places split into lobes. Engineers plan around it the way sailors mark reefs. But reefs don't usually move this fast, and when they do, your satellite TV, weather data, and rideshare map learn new dead zones the hard way. Magnetism is the messenger from the core. Down there, the liquid iron outer core flows in tangled loops under pressure and heat, and those flows generate the field, our dynamo. When the inner core's relative motion shifts, when heat moves unevenly across the core-mantle boundary, the flow reorganizes. Think of a giant metal lava lamp where the currents aren't soothing. They're the wires of a planet-sized generator. Tweaks in the flow change where the field is strong, where it's weak, and which way the poles drift. Meanwhile, something else was happening above our heads. The auroral ovals, the rings around each pole where charged particles rain down, wandered. Not wildly, but enough that airports and airlines updated thresholds for rerouting. Space weather storms hit the same grids differently depending on the field's current mood. A storm that would have been a shrug 30 years ago becomes a problem when a regional field is already softened. This is why. Grid operators watch K indices like hawks and keep transformer spares in warehouses they hope never to open. Here's a human moment. A satellite operator walked into a morning stand-up with a stack of anomaly reports. Most were tagged SAA. The team had built extra memory scrubbing into passes over that zone. Lately, the box labeled SAA didn't fit. Anomalies showed up just outside the old contour, nibbling at the edges. The operator pulled up the latest magnetic field model and drew a new line with her finger. We either expand our safe mode window or we start budgeting for early failures. The room got quiet. Budgets are louder than auroras. What nobody knew at the time, the inner core had already started lagging the mantle. The dynamo doesn't flip overnight, but flow patterns don't keep promises either. If heat flux at the core-mantle boundary shifts, say because mantle structure channels heat unevenly, the outer core's current loops bend and stretch. Regions like the South Atlantic anomaly are where reversed flux patches at the core's top project to the surface, thinning the field above. The core's slowdown doesn't cause the anomaly to grow by itself. It's part of a choreography where differential motion, heat flow, and boundary topography share the floor. This was the moment everything changed in how we read the sky. For years, the SAA was treated like a static dent with an inconvenient address. Then Swarm's maps made clear it was evolving. The North Pole Sprint forced mid-cycle world magnetic model updates in 2019. Compasses in northern cities needed redeclination headlines. Aircrews started seeing aurora farther from the poles than their training slides implied. None of these demanded doomsday. They demanded better forecasts and a respect for a field that breathes and bills that arrive when flights reroute and satellites glitch. Let's demystify the engine in one breath. Moving conductive fluid in the outer core generates magnetic fields. Those fields interact with the flow and with the solid inner core, which itself is slightly asymmetric and grows by freezing iron onto its surface, releasing heat and light elements that feed convection. The mantle above is not a passive blanket. It extracts heat unevenly, imprinting patterns on the dynamo. Slow the inner core's relative spin, and you tweak the timing of that feedback. Over years to decades, the loops of current shift and the surface field shows it. Impact lands where you feel it. Satellite manufacturers add shielding, accept mass penalties, and design firmware to survive. Passes through the anomaly. Airlines coordinate with space weather centers to limit dose on high-latitude routes when storms and weak fields stack up. Grid operators rehearse storm playbooks, monitor geomagnetically induced currents, and argue over transformer standards that trade cost for resilience. Biologists watch animal navigation studies for disorientation trends. And yes, people step outside when the aurora creeps south and say it's beautiful. It is. It's also a status report. Your sky is telling you how the engine is running today. Caveats matter. The field has waxed and waned for as long as rocks have recorded it. It drifts. It sometimes reverses polarity on timescales of thousands of years. A growing anomaly doesn't guarantee a flip, and a pole sprint isn't a countdown clock. But when you line up the slowdown in the inner core, the reorganizing flows that a dynamo must follow, and the surface maps we can measure right now, the pattern is hard to ignore. The messenger is talking. The question is whether we're listening. Magnetism told us the engine is twitchy. To see how those twitches turn into pressure points you can feel under your feet, we need to watch stone take a breath. Clue 3. Earthquakes don't roll dice. Stone doesn't care about headlines, but it does keep score. Along subduction zones, plates grind, lock, and load for decades. When they finally slip, we call it a surprise. It isn't. It's a release scheduled by physics and delayed by friction. Here's the part people miss. Even tiny nudges, imperceptible changes in stress, can advance or delay that appointment by years. A millisecond change in Earth's rotation won't snap a fault by itself. But on a fault already primed, it can act like a finger on a domino, an invisible push with very visible consequences. Start with the stakes. Clusters of megathrust earthquakes don't just redraw coastlines. They reroute economies for a generation, supply chains shatter, ports sink a few centimeters and change which ships can dock, insurance markets panic, aftershocks drag rebuilding into a fog of uncertainty. The choice to bolt a bridge joint differently, to move a hospital backup generator uphill, or to teach a child a higher staircase matters more in clustered decades than in quiet ones. Now, what actually happened? Look at the historical record, and you see periods when the planet seemed to exhale in bursts, the early 1960s. With multiple giant quakes in Alaska and Chile in the long shadow of Earth's rotational slowdowns. The 2004 to 2011 run from Sumatra to Tohoku, with several great ruptures stepping along subduction arcs. Scientists noticed that some of these clusters loosely lined up with intervals when Earth's rotation decelerated on multi-year scales. The logic is simple physics: slow to spin a hair, and angular momentum shifts. The solid Earth, oceans, and atmosphere share that bookkeeping. The redistribution changes the centrifugal bulge and slightly adjusts how weight is borne across latitudes. That changes Coulomb stress, minutely, on some faults. Before we go further, a guardrail. Correlation isn't causation. Many years of slow rotation didn't produce large quakes, and many large quakes arrived with no rotational nudge in sight. The mainstream view is cautious. Still, when researchers remove the known drivers, winds, ocean currents, seasonal hydrology, there's a leftover signal consistent with interior torques and mass shifts that can, in principle, modulate fault stress. Not force the issue, modulate it. Here's a human moment from a coastal town that lives with sirens. The school gym wall has a painted line at shoulder height. Run to here. Every spring, kids jog evacuation routes in sneakers that squeak. Parents bake muffins and quietly check their radios. That same town's tide tables were updated last year with a new twist, adjusted for vertical land motion and slight rotation changes. The highest tides arrived 3 minutes off old expectations. Nobody writes a poem about 3 minutes. Emergency managers do. 3 minutes moves a traffic light cycle from helpful to harmful, and it's happening now. Meanwhile, something else was happening beneath our feet. Slow slip events, silent earthquakes that release energy over weeks, showed up more often along certain segments in years when rotation, hydrology, and even distant seismicity seemed to conspire. In Cascadia and Hikarangi, GPS networks watch the crust breathe. These slow slips can load or unload adjacent locked patches. Think of them as the planet testing a door latch. If the latch is almost open, a nudge matters. What nobody knew at the time was exactly how the interior torque budget stacked with all the surface players. But we know the coupling exists. Electromagnetic and topographic coupling at the core-mantle boundary can change Earth's rotation by tiny amounts over years. Those tiny changes slightly reshape the equatorial bulge and adjust stresses. It's the kind of effect that wouldn't matter to a fresh, unlocked fault, but can matter to a century-loaded interface that needs ounces, not pounds, to give. Action is where this gets real. In the wake of the 2011 Tohoku quake, hazard modelers revisited locked segments from the Kuril Islands to Hokkaido and down the Japan Trench. They updated recurrence intervals not because of a cosmic metronome, but because clustered strain release changes whose next in line. In Sumatra after 2004 to 2005, the sequence marched northwest, each rupture altering stress on the next patch. Was rotation in the room? Maybe as a whisper among louder voices. Aftershock redistribution, viscoelastic mantle flow, post-seismic creep. But when you're calculating risk for ports in Padang or cement plants near Banda Aceh, whispers add up. Impact shows up as policy. Building codes in Wellington debated basin amplification and column ductility after revised clustering probabilities raised near-field shaking odds in certain windows. In Chile, utilities redesigned substation anchors after liquefaction models updated by new recurrence estimates. In Alaska, emergency planners moved fuel depots off soils that amplify long-period shaking. Not because someone predicted a date, but because the dice aren't fair forever. Here's where we're honest. Scientists split on whether multi-year rotation anomalies meaningfully correlate with global M8+ frequency. Some analyses suggest mild clustering after deceleration intervals. Others find no robust signal once you trim the data and correct for catalog completeness. The safer ground is local. Stress changes from any source. Post-seismic deformation, hydrological loading, rotational tweaks can change probabilities on specific faults by small percentages. Small isn't zero. For a megacity, 1% is policy. Meanwhile, across town, a harbor engineer stared at a simulation that combined sea level rise, glacial, isostatic rebound, and updated earthquake recurrence. The seawall plan on his desk assumed another 15 quiet years. The model disagreed. He changed the crest height by 30 centimeters and added a second pump. That's what earthquakes don't roll dice looks like in budget line items. So this was the moment everything changed in how we talk about quakes. Not prophecy, but conditioning. The planet's rotation, the breathing mantle, the loaded faults, the rising water, all in one ledger. If you want to feel the push, we have. To step deeper, to the handshake, where momentum moves uphill and the engine sends its shiver to stone. The hidden handshake, core-mantle coupling. To feel the push, stand at 2,900 kilometers down, where hot rock ends and liquid metal begins. That boundary, the core-mantle boundary, is the handshake. On one side, the outer core, a conducting ocean of molten iron, sliding and circling. On the other, the base of the mantle, rough as an old mountain range flipped inward, studded with highlands and basins we call ultra-low velocity zones, and large, low-shear provinces. When those two surfaces move past each other, they trade momentum. It's not a shove, it's years of steady pressure, like a glacier teaching a valley its shape. Here's why it matters. The mantle is most of the planet's mass, so tiny changes in its spin are expensive. The core is small by comparison, but fast and fluid. It can flex its flow to pay small debts quickly. The trade happens through two main channels. First, electromagnetic coupling. The moving iron in the outer core generates magnetic fields, and those fields thread into the electrically conducting base of the mantle. If the mantle drifts a bit faster or slower, those field lines drag it like a magnetic brake or clutch, transferring torque. Second, topographic coupling. The boundary isn't smooth. Imagine mountain ridges and canyons on a metal ocean's floor. As flow in the outer core sweeps over that topography, pressure variations push on the mantle's bumps and troughs, adding another route for torque to cross the line. Now layer heat. Heat leaving the core isn't evenly distributed. The mantle above has continents, plumes, and chemistry that channel heat differently by longitude. Where heat extraction is stronger, outer core fluid cools and sinks. Elsewhere, it rises. That pattern convection organizes loops of flow that both power the dynamo and set how the outer core drags on the inner core and rubs on the mantle. So when the inner core begins to lag the mantle, the timing of those loops shifts. The handshake adjusts its grip. A micro story from a lab bench. A team runs a spherical quet experiment, two nested spheres, fluid in between, magnetic field imposed. When they slow the inner sphere by a hair, the magnetic torque spikes for a moment, then settles to a new, stubborn value. It's not a perfect Earth, but the behavior rhymes. Differential motion reconfigures flow, and the coupling finds a new balance. The lesson wasn't Earth is a beaker, it was clutches slip then bite. Meanwhile, something else was happening overhead. Satellite maps of the geoid, the shape you'd get if oceans could rest perfectly, picked up minute changes. Some of that is water and wind. Some is the mantle creeping, relaxing after big quakes. But buried in the signal are tiny hints of long-period rotation changes, consistent with torques at depth. You won't find a headline in a tenth of a milliarc second. You find a ledger entry. Energy moved here. This was the moment everything changed in our model. We stopped thinking of Earth's layers as stacked pancakes and started treating them as gears with greasy teeth. The electromagnetic gear is messy. Field lines slip, conductivities vary, induction delays torque like a rubber band. The topographic gear is stubborn. Change the boundary shape by long-term growth at the inner core or chemical piles at the base of the mantle, and you change how the fluid bites. Neither gear is big alone, but over decades, they add up. Stakes? The torque that crosses this boundary is the same torque that tweaks day length, shuffles stress, and nudges the dynamo's loops. It touches ocean circulation subtly through rotation rates. It leans into climate cycles by timing small angular momentum trades with atmosphere and hydrosphere. The handshake doesn't cause storms or quakes outright. It sets the background tempo they play against. Action looks like this. The inner core slows relative to the mantle around 2008. Outer core flow reorganizes to keep the dynamo humming. Magnetic coupling to the lowermost mantle adjusts, transmitting a slightly different torque. The net planetary spin responds by thousandths of a second. The equatorial bulge relaxes or stiffens imperceptibly. Faults that are already near failure get a marginal stress nudge. Satellites see field maps drift, timing labs see the millisecond breathe. Nobody's coffee spills. Engineers update a spreadsheet. Impact arrives in ripples. On short timescales, winds and tides dominate angular momentum. On multi-year to decadal scales, the core-mantle handshake sets the floor those faster players tap dance on. That's why the residuals, what's left after you subtract weather and waves, matter. They're the handshake's signature. Caveats belong here. We can't put sensors at the boundary. We infer through seismology, geomagnetism, and rotation. Models disagree on how rough the boundary is, how conductive the deep mantle truly is, and how much torque each mechanism carries. But every independent line, repeating earthquake timing, normal mode wiggles, swarms field maps, length of day residuals, points to a live coupling that breathes with decades. So the story is simple and stubborn. Two layers meet, they trade momentum, and the rest of Earth listens. If the engine is bogging down, the clutch is where we feel the grind, which begs a blunt question. What's changing inside the furnace that makes the clutch slip differently now? Inside the furnace, why the core would slow. If the clutch is slipping, something inside the engine changed. Start at the center, a solid inner core of iron nickel that's still growing. Every year, a whisper-thin shell freezes onto its surface as heat leaks out and iron crystallizes. That freezing releases two things that keep the dynamo alive: latent heat and lighter elements like sulfur or oxygen that buoyantly rise. Both drive convection in the liquid outer core, but growth isn't uniform. If one hemisphere of the inner core grows a little faster, because the mantle above extracts more heat there, its shape and texture become uneven. That asymmetry can change how the inner and outer cores drag on each other, and how the whole stack couples to the mantle, slow the relative spin of hair, and the flow reconfigures to a new balance. Now layer viscosity, the unsung character here. The inner core isn't a perfect crystal. Seismic studies hint at anisotropy, mushy regions, maybe even zones with different grain sizes. Viscosity controls how easily the inner core can deform or creep when torques act on it. If over decades temperature and composition shift enough to raise effective viscosity, the inner core resists being tugged along by the outer core's magnetic grip. That resistance shows up to us as a slowdown relative to the mantle. The torques are the same songs, the instrument strings got tighter. Meanwhile, heat has to leave the core to keep convection going, and the route out is through the mantle. But the mantle isn't a passive radiator. It's patchy. Superplumes under Africa and the Pacific, subducted slabs pooled near the boundary, and chemical piles that act like insulation. Where the mantle extracts more heat, the outer core cools, sinks, and accelerates flow. Where it insulates, flow slackens. That heterogeneity can shift the map of upwellings and downwellings in the core, changing which loops of current dominate. A rebalanced flow pattern might grab the inner core differently, nudging its rotation rate. Here's where another suspect walks in. Electromagnetic torque depends on the deep mantle's electrical conductivity. If regions at the base of the mantle, enriched with iron-bearing minerals or partially molten patches, conduct better than we thought, they provide a stronger magnetic clutch. Improve the clutch in one longitude band, and you bias how torque transmits. Over years, that can impose a phase on the inner core's drift, pushing it toward a slower relative spin. Topography at the core, mantle boundary plays the muscle role. Seismic imaging has mapped ultra-low velocity zones, pancake-thick, iron-rich blobs that protrude into the outer core. They're speed bumps for fluid. As jets in the outer core shear past those bumps, pressure patterns add or subtract torque on the mantle and on the inner core's magnetic linkage. Change the bumps by piling more subducted oceanic crust into one region over millions of years, or by thermochemical reshaping, and you change the long, slow drag. Add composition to the ledger. As the inner core freezes, it expels light elements into the outer core, stratifying the top of the core if mixing can't keep up. A stably stratified layer, think of it as a thin, less turbulent cap, would suppress some convective motions near the boundary. That can decouple parts of the outer core from mantle torques, altering the spectrum of flows that reach down to shear the inner core. It's another way to weaken the hands on the wheel and let the inner core fall slightly behind. A micro story from high pressure. In a diamond anvil cell, an iron alloy sample at core conditions refused to behave like the models. Its thermal conductivity came out higher than expected. Higher conductivity means heat escapes the core, more efficiently if the mantle allows it. Better heat transport can either invigorate convection or, paradoxically, thin the driving temperature gradient if the mantle caps the flow. The experimentalists rewrote a line in their code, and a simulation that used to keep the inner core locked to a steady differential rotation now settled into a slower beat. Other suspects live above the boundary. Changes in mantle flow that most of us notice as hotspot drift or plume pulsations also change the heat flux pattern felt by the core. Superplume growth or waning tweaks the thermal wind in the outer core. Subducted slabs pooling asymmetrically on the boundary act like cold fingers, focusing downwellings. The dynamo listens to those fingers. The inner core feels the echo. Could the sun or the moon be in this story?
tides.
From both bodies pump energy through the oceans and even the core, modulating flows slightly. On short time scales, tides dominate day-to-day angular momentum trades. On decadal scales, they provide a steady background rhythm that the core rides on. Their role here is timing, not authorship. Impact, a slower inner core relative to the mantle retunes the dynamo's choreography. Field lines drift differently, weak spots migrate. The pole's path curves a bit more or less. The torque across the boundary adjusts, nudging the length of day by thousandths of a second. None of this breaks breakfast. Over decades, it shapes which satellites retire early, which flights detour, and which faults feel that extra ounce on the scale. Caveats keep us honest. We can't drill to the core. We infer from seismic waves, magnetic maps, and rotation residuals. The 2024 Nature study pins the slowdown. Lab work constrains conductivities. Models explore plausible couplings. Some parameters, like exact deep mantle conductivity or boundary roughness, still carry wide error bars. But the simplest explanation that fits the observations is a real change in the engine's internal balance. Uneven heat loss, evolving inner core structure, and mantle boundary conditions combining to ease the inner core's foot off the gas. Surface telltales, the signals you can actually see. Okay, you asked for proof on the surface. Here's the dashboard you can point at without a PhD. The places where the deep engine's mood shows up as little glitches in ordinary life. Start with the sky. The auroral oval has been drifting and breathing in ways pilots feel in their flight plans. Airlines that love polar shortcuts now watch dose meters and space weather bulletins like weather radar. When the field softens regionally, storms that used to be pretty but harmless nudge into reroute and call dispatch. If you're far from the poles and you're seeing aurora headlines more often, that's not a prophecy of doom, it's the field mapping out loud. Meanwhile, satellites have become reluctant witnesses. Over the South Atlantic Anomaly, operators schedule memory scrubs, widen safe mode windows, and budget for extra shielding on future birds. You don't need their dashboards to see the effect. You can watch mission timelines slip and hear about anomaly passes in earnings calls. Lately, those safe mode boxes have crept wider because the dent isn't staying put. Format it this way. When a satellite's firmware treats a chunk of sky like a pothole, and the pothole slowly shifts, something underneath is moving. Compasses tell a quieter story. In northern cities, surveyors update declination more often than their grandparents did. Some local governments pushed out, "Your compass is wrong by X degrees" notices for hikers and first responders because the North Magnetic Pole's sprint rewrote old maps mid-cycle. It's a small alert with a big subtext. The field model you learned in school expired early. Now look at drag. Yes, air drag. When the upper atmosphere puffs up during geomagnetic storms, satellites feel it. Lately, operators have seen drag spikes that don't match the old playbooks because field changes alter how energy couples into the atmosphere. It's not the core alone, it's the stack. But when you see more frequent station-keeping burns clustered over familiar longitudes, you're staring at a surface effect with roots below. On the ground, magnetometers in university basements and high school rooftops record daily jitters and storm surges. Stitch them together worldwide, and you get a real-time heartbeat of the shield. You can track this yourself, the data's public. Watch how certain latitudes light up faster now during solar events than they did a couple decades ago. The pattern tells you where the field is thinning and where currents are likely to bite into grids. There's a subtler gauge, gravity maps. The GRACE and GRACE-FO satellites measure tiny shifts in Earth's gravity field as mass moves around. Water in aquifers, ice melting off Greenland, even the oceans sway. They also pick up minute changes tied to Earth's rotation residuals. You won't see a tidy core label on a gravity plot, but you will see fingerprints when mass redistribution upstairs stacks with rotation tweaks from downstairs. Coastal planners quietly use these datasets to time dredging, to site new piers, to set floodgates. The reading on their face when a line trends the wrong way, that's a tell. Sea level carries another whisper. Global mean sea level rises for climate reasons, but regionally, the ocean tilts in response to gravity and rotation. A slight slowdown can shift where water piles up by a few millimeters. Tide gauge custodians have started tagging these fingerprints, tiny but real, on top of subsidence and storm surge. When you're deciding whether to raise a seawall one more course of concrete, those millimeters join the argument. Animals are in this story too, not as omens, but as data points. Biologists logging turtle hatchlings and homing pigeons, See bouts of navigation, weirdness that cluster in time with local field wiggles. Nobody's blaming the inner core for a confused bird. Still, when the field map changes faster in certain corridors, the creatures that fly blind by magnetism tell you first. Put that alongside the magnetometers and the satellite anomalies, and the chorus starts to harmonize. Here's a human micro-story. A bush pilot in Nunavut carries 2 maps, a topographic chart and a declination insert printed 6 months ago. He flips the insert more often now because the runway headings don't quite match the old stencil paint. The airfield manager orders new numerals for the threshold. It's a paint job with a planetary footnote. What can you actually watch without special access? 3 feeds. 1. Length of day updates from the International Earth Rotation Service. If the residual line bends against the usual seasonal push, make a note. 2. The European Space Agency's swarm mission field models. Watch the South Atlantic contours and the pole's path update. 3. Global magnetometer networks and space weather alerts. See how often mid-latitudes light up. Add an airline advisory report for polar routes and a couple of satellite operator blogs, and you've built a dashboard. Impact shows up in invoices. Satellite insurance premiums edge up for missions with heavy South Atlantic exposure. Airlines add fuel to skirt high-dose corridors during solar peaks. Grid operators invest in new monitors for geomagnetically induced currents and quietly trial transformer designs with better cores. City planners adjust compass-based surveying protocols. None of this screams. It accrues. Caveats again. These are indicators, not smoking guns. The Core's slowdown is one player in a crowded band, but if you're building a watch list for the next decade, these surface telltales are your dials. Auroral latitude shifts, SAA footprint and anomaly rates, compass declination updates, drag spikes, magnetometer storm reach, and those tiny rotation residuals. Signals are cool, consequences are loud. Cascading risks, grids, GPS, flights, and finance. Signals are cool, consequences are loud. Start with the grid. High voltage lines sprawl across continents like giant antennas. When space weather drives currents through the ground, those lines pick up slow surges, geomagnetically induced currents that don't trip breakers, but quietly saturate transformer cores. In a softened field, storms couple more efficiently. The risk isn't Hollywood sparks, it's heat. Windings run hot, insulation ages. Dissolved gases show up in oil tests. And a unit that should live 40 years dies at 20. Spares are scarce and huge. You don't fly one in overnight. You wait months. That wait is the real blackout. Action looks like this. A storm warning hits. Operators lower power transfers on vulnerable corridors, bring peaker plants online to keep flows local, and watch current sensors that didn't exist 2 decades ago. They coordinate with space weather forecasters the way coastal towns track hurricanes. If the anomaly footprint expands, the same storm that once brushed the northeast now bites deeper into Quebec, Scandinavia, or New Zealand. Utilities that learned from 1989 and 2003 order better transformer cores, add neutral blocking devices, and rehearse manual switching routes. It's not panic, it's choreography under stress. Impact lands in invoices and headlines. A region avoids a cascade, but spends millions in overtime and lost industrial production. Insurance asks for mitigation proof. Regulators ask for plans tied to thresholds. KP this high, reduce flows by that much. Meanwhile, a mid-latitude city that never cared about Aurora learns what a geomagnetically induced ampere looks like. GPS next. Precision timing is the quiet spine of modern life. GPS doesn't just tell you where, it tells every cell tower, bank server, and data center when. A jitter of tens of nanoseconds unlocks or breaks networks. During storms, radio noise, and ionospheric turbulence scramble signals. A weaker, patchier geomagnetic shield lets more energy into the upper atmosphere, making that turbulence worse and less predictable. Receivers lose lock, multipath errors grow, and timing oscillators have to coast. Most coast fine for a bit, some don't. Meanwhile, something else was happening in the supply chain. Farmers that use real-time kinematic GPS to plant within centimeters watched drift spike during active geomagnetic days. Their lines wobbled, seed went in slightly off. A month later, the rows told the story. Construction crews staking a bridge pier saw survey fixes drop out and had to reoccupy points. A financial exchange's backup time source kicked in, added microseconds of error, and tripped an internal alert. Nobody lost $1 billion, but risk managers took notes and bought a second independent clock. E-Lauren here, fiber-based PTP there, rubidium in the rack. Flights are where the sky writes policy in real time. Polar routes save time and fuel, but they fly through radiation and patchy HF radio. Airlines already detour during big solar events. With the field evolving, the same event pushes dose rates higher on certain tracks and messes with comms more often. Dispatchers reroute south, add fuel, accept delays, and hit crew duty limits. A long haul becomes a two-stop puzzle. Medical guidance tightens for pregnant crew. Pilots brush Aurora at latitudes their training slides didn't list. The cabin cheers. The cockpit checks checklist 32B. Satellites live where the risk compounds. Over the South Atlantic Anomaly, onboard computers flip into safe mode more often. Star trackers lose the sky longer. Drag spikes from geomagnetic heating force extra burns and eat propellant budgets. Anomalies near but outside the old SAA contour creep into mission logs. Operators widen do not do sensitive stuff boxes and shift instrument schedules. A climate satellite loses a month of clean data to noise it can't calibrate out. A small Earth observation startup loses 2 CubeSats early, not to a single storm, but to a lottery of cumulative hits. Their board learns the phrase, radiation hard. Finance is timing with a dress code. Clearinghouses and exchanges align trades to clocks that assume GPS behaves. When it doesn't, phase-locked loops grumble. Regulations already require traceable time. Now compliance teams simulate storm days and test holdover. A micro jitter that would have been shrugged off in 2015 triggers circuit breakers in 2026 because the risk appetite changed. Banks add more atomic clocks and cross-check time over fiber routes that don't go through the same duct. It's not because the inner core slowed, it's because the slowdowns downstream make storms messier and timing more fragile. Here's the human beat. A grid control room night shift watches magnetometer screens glow. A dispatcher in a windowless office moves lines on a digital map, hearing only fans. An airline ops lead at 3 a.m. texts 4 captains to divert and apologizes for crew rest math. A satellite engineer schedules extra memory scrubs for the week and sends a weary emoji. A CFO signs off on a transformer order with an 18-month lead time and hopes the old one holds. A farmer looks down a crooked row and blames the sky. Yes, your crypto depends on molten iron behaving itself. Mitigation isn't glamorous. It's transformer spares and blocking devices, dual source timing, HF fallback and SATCOM backups, autonomous flight planning that ingests space weather feeds, satellite hardening, and ops teams drilling. It's regulators tying thresholds to actions. It's insurers lowering premiums for proof of resilience. It's boring until the night it isn't. Meanwhile, the planet's stress meter keeps ticking up. Megathrust math. If stress tips, who hurts first? Here's where we stop talking in generalities and start naming coastlines. If the background torque and rotation tweaks are whispering into already loaded faults, which arcs hear it first? Start with the places that store stress for a long time and release it in chapters. The Pacific Rim holds most of the world's megathrusts, but they don't all behave the same. Some rupture often in moderate pieces, others lock hard and go quiet for a century. The quiet ones scare planners. Cascadia first. From Northern California to Vancouver Island, GPS networks show a slab that's mostly locked, breathing in slow slip pulses every year or two on its northern half. Those slow slips don't break cities, but they load and unload nearby locked patches. Paleotsunami deposits, sand sheets, and coastal marshes mark great ruptures roughly every few centuries, with clusters in some intervals. The southern segment near Oregon's mid-coast and Northern California is a candidate for an earlier release than the north, because it appears more persistently locked and carries fewer slow slip pressure reliefs. Add sea level fingerprints and subsidence, and a south first scenario becomes a policy lever. Hospitals inland, bridges with longer period damping, evac routes rehearsed. Across the ocean, Japan's Nankai Trough telegraphs in pairs. Historical records show linked ruptures, Tonenkai and Nankai, sometimes within months. Strain has rebuilt since the 194's Pifty sequence. Offshore drilling and seafloor cables watch fluid pressures and crustal motion in real time. If subtle rotational nudges matter anywhere, it's here, where the difference between a partial and a full-length cascade changes who gets 3 meters of vertical shift. Shikoku's offshore segments have crept in patches. The gaps are the worry. A full arc rupture would slam the Kii Peninsula and Tokai coasts. Planners argue about seawall heights with spreadsheets, not slogans. Sumatra's Sunda arc still carries after images from 2004 to 2005, but farther south, the Mentawai patch remains locked. Coral microatolls, living tide gauges, record uplift and subsidence with yearly rings. They flagged uneven loading that sets the stage for another big step. A Mentawai event isn't just Padang's problem, it's an Indian Ocean Basin problem for waves and cables. Chile is a long ledger. The 2001 Mal quake didn't empty the bank. North toward Valparaiso, segments ruptured in 2014 and 2015, but the gaps around La Serena and Coquimbo retain concern. Southward, Concepcion to Araco Eyes posted 21 adjustments. Chile's building codes are among the world's best because they learned the hard way that clustering is real. A millisecond of rotation won't pick a date. It can be the feather on a stack of anvils. Alaska's Aleutians bend from the 1964 scar into segments with varied behavior. The Shumagin Gap has been called creeping. It still hosts surprises. Farther west, the Andreanof Islands locked patches stare at sparse tide gauges and better satellites. Uplift/subsidence patterns combined with new recurrence estimates have small towns moving fuel depots uphill. The lesson isn't dread, it's logistics. The Indian Ocean's other flank, the Makreen subduction zone off Pakistan and Iran, is the quiet cousin with a bad memory. An 8-class event in 1945 sent a tsunami into Karachi. Sediment cores hint at bigger prehistoric waves. Makreen's thick sediments can amplify tsunami heights even for moderate slip. Ports, refineries, and flat deltas compound exposure. Early warning here is thin. Adding seabed instruments is a cheap win. Mediterranean subductions, Hellenic, Calabrian, and the Caribbean's Lesser Antilles don't headline Megathrust lists as often, but their tsunamis hit crowded coasts with minutes of warning. The Hellenic Arc's historical catalog includes M8-ish events. Crete and Rhodes carry tsunami stories in stone. Meanwhile, Lesser Antilles segments host slow slip and volcanoes. Stress transfer there is a braid. A clustered decade would stretch civil protection thin. Now the math you can use. We can't forecast dates. We can rank windows by raised probability, combine locked patch maps from GPS, paleo records of recurrence, slow slip timing, vertical land motion, and inundation modeling. Then apply small probability deltas for multi-year rotation deceleration intervals. Those deltas are single digits. For a megacity, that shifts cost-benefit lines. Seawall crest plus 30 centimeters, hospital diesel moved to the roof, schools drilled twice instead of once. Preparedness isn't a siren, it's procurement. Here's a micro story. A coastal city's seawall plan assumed a 1 in 500 year wave. New trench coring shaded the interval to 1 in 350 with wide error bars. Add a small bump for decadal loading signals, and the council approved 1 extra pump station and a 20-minute earlier evacuation trigger. It cost them a bike lane redesign. No one cheered. In 10 years, someone might. Stakes tied to people. Ports in Valparaiso, Osaka, Padang, and Karachi aren't dots. They're food, medicine, and jobs. Building codes decide whether families go home after a quake or move for a year. The math is cold. The outcome is warm if we act. Caveats keep us straight. Rotational effects are small, and local geology dominates. But risk is addition, not a guess. Locked faults, sea level rise, subsidence, poor soils, and fragile grid stack. A smart decade shifts what's stackable. Everything was about to get weirder because ice and oceans join the story and start moving weight around. Ice, water, and weight. Climate's feedback on the engine. While we were tracing torque and fault stress, ice and oceans pulled up a chair. Mass moves, Earth answers. Shift enough water or melt enough ice, and you change how the planet spins by tiny amounts, where the crust flexes, and which faults feel the extra ounce. It's not a new force. It's another hand on the same steering wheel. Start with Greenland. Each summer, meltwater pours off the ice sheet, and each year lately, a little more mass leaves for the ocean. Antarctica moves slower, but holds the bigger lever. When it shelves thin and grounded ice retreats, the oceans inherit that weight. Add groundwater pumping in dry regions and dam filling in wet ones, and you've got a global shell game. Mass leaves high latitudes, piles in basins, and the whole planet adjusts its balance. Action looks mundane. Gray satellites watch gravity shift month by month. The International Earth Rotation Service notes micro changes in the length of day and the wobble of Earth's spin axis, the Chandler wobble and seasonal pole drift. On years with strong hydrology swings, the pole meanders differently, and the tick of Earth's rotation stretches or squeezes by fractions of a millisecond. On maps, sea level doesn't rise like a bathtub, it tilts. Where gravity strengthens, near big melt sources that lose their pull, water actually drops locally while piling far away. Those sea level fingerprints decide which ports worry sooner. Meanwhile, the crust breathes. Lose an ice load and the bedrock rebounds. Glacial isostatic adjustment. Scandinavia rises millimeters a year. Parts of Canada do too. Around Greenland, GPS monuments move like slow pistons, recording uplift as ice thins. That lift changes stress on faults nearby and far, because the lithosphere is an elastic shell with a long memory. In West Antarctica, the story inverts. Grounding lines retreat, water loads coastal shelves, and the flex pattern shifts. No alarms ring, but the stress ledger updates. Here's the stakes beat. Add these mass moves to the core, mantle torque background, and you get timing windows when many small stresses align. Not enough to predict a rupture, enough to shade probabilities. A subduction interface already loaded by decades of plate motion feels an extra nudge when the equatorial bulge relaxes slightly during a rotational slowdown and a regional hydrology swing leans mass toward one latitude band. Each effect is tiny. Together, over years, they can matter for the next percent in a hazard model, a micro story from a river delta. Engineers designing a new floodgate near Ho Chi Minh City stared at a line that refused to be straight. Sea level at their tide gauge rose faster than the global mean because of subsidence and regional fingerprints. Then the day-length residuals bent. The spring tide arrives here, curved by a hair. They advanced a gate-close trigger by 5 minutes. That's climate talking to rotation while a city listens. Ocean circulation joins in. When the field weakens regionally, geomagnetic coupling with the upper atmosphere changes, which during storms alters how energy reaches the thermosphere and trickles down to density and winds. Those winds and pressure fields steer where the ocean heaps up during storms. Storm surge models now ingest KP indices and polar cap potentials alongside barometer tracks. The ocean isn't reading the core's diary, but it's reacting to the same space weather and rotation frame. The core helps set. Meanwhile, something else was happening under the ice. In Antarctica's Amundsen Sea, warm water nibbles Thwaites Glacier's underbelly, changing buttressing and stress chains inland. Uplift lags behind retreat. The crust is slow to spring. That delay keeps stress patterns out of sync with the loading that caused them, adding another phase to the planet's long metronome. Stack that with a decade of inner core lag and you get an interference pattern. Constructive some years, destructive others. This is where the analogy lands. Think of a mattress with dents. Slide a heavy box from one corner to the other and the springs creak. The shape changes, the person on the edge feels it in their hip. Earth's springs are the mantle and lithosphere. The box is ice and water, and the hip is a city on a fault. When the box slides slowly and the springs are already tired, even a small shift finds nerves. Impact shows up in planning. Tokyo's tide and surge maps incorporate regional fingerprints from Greenland, plus subsidence from local fill, plus rotational residuals that move tide peaks by minutes. New York's flood maps bake in sea level tilt from Antarctic melt. Wellington's earthquake drills quietly move dates to line up with local slow slip seasons and spring tides. Not because the core ordered it, but because risk stacks better when cycles rhyme. Open question. Could overlapping cycles synchronize into bad decades? That's the quiet fear, not a headline. Core-Mantle, torque drifts, decadal hydrology swings, El Niño, La Niña mass shifts, solar cycles pumping space weather, and ice loss accelerating. Each small alone, occasionally aligned together. Scientists aren't declaring a synchrony clock. They're building dashboards that show when needles lean the same way. Those dashboards decide when to pre-position transformer spares, when to widen polar flight buffers, and when to pour the next layer onto a seawall before the budget window closes. Honesty check. Hydrology and climate dominate year-to-year angular momentum more than the core does. On decadal scales, both sing audible harmonies over the engine's hum. The science is still partitioning credit. How much of a given residual belongs to groundwater depletion versus ocean mass versus interior torque? But if you live where water meets stone, you don't wait for perfect attribution. You instrument, you pre-commit to thresholds, and you move when the needles lean together. To test whether these cycles have lined up before and what followed, we've got to leave the instrumental age and read the long memory written in trees, rocks, and mud. The long memory, paleo records, and ancient disasters. To test whether cycles ever lined up before, we have to let rocks and mud speak. They don't shout, they hum. Start with lava that cooled under the sky. As it froze, iron grains inside aligned with the magnetic field like tiny compass needles, locking in direction and strength. Stack enough flows, and you get a flip book of the field's mood over tens of thousands of years. Some chapters show a weaker shield, patchier than today, not doom, context. Tree rings add weather to the chorus. When the field slackened, cosmic rays punched deeper into the atmosphere, boosting production of carbon-14 and beryllium-10. Those isotopes land in wood and ice. Count rings in bristlecone pines, measure 14 sea bumps, and you see past radiation surges. Drill Greenland or Antarctic ice, assay B10, and you see the same pulses in frozen air. Two very different archives nod at the same years. That's not prophecy, that's a cross-check. One interval stands out, roughly 42,000 years ago, the last Champs excursion. The field didn't flip permanently, it stumbled, dropping to around a tenth of normal for a few centuries. Auroras likely crept far from the poles. B10 spiked in ice. If you're expecting global cataclysm, that's not what the sediments say. Life didn't blink out, but climate nudged, ozone chemistry shifted, and any satellite we'd fly today would hate that decade. The point isn't repeat incoming, it's weak fields are livable but noisy. Closer to home in time, stalagmites, the slow drips that build stone inside caves, record the chemistry of the water that fed them. Some lock in trace isotopes that track rainfall shifts tied to solar forcing and geomagnetic shielding changes. One cave in China carries a signature of a geomagnetic burp about 2,500 years ago that lines up with B10 peaks in Greenland. Different cave, different continent, same tick. Meanwhile, ancient ovens and kilns preserve archaeomagnetism, the direction and intensity of the field when clay was last fired. Map those across the Mediterranean, and you see regional intensity surges and dips over millennia that match models of a twitchy dynamo. What about earthquakes and eruptions? Did they cluster during weak field windows? The honest answer, the record is noisy. Coastal sand sheets in the Pacific Northwest mark great Cascadia tsunamis every few centuries, with some clusters. Japanese chronicles track Nankai pairs, Mediterranean tsunami deposits tied to Hellenic arc slips. Volcanoes leave ash in lakes with datable layers. Hekla, Santorini, Topo, Toba, farther back. Some clusters overlap intervals of higher cosmogenic isotopes and rotation wobbles inferred from varved sediments. But dating uncertainties and sparse archives make clean links hard. Pattern, not prophecy. Here's a micro story from a lakeshore. In Chile, a quiet lake holds a layered mud cake. Every year lays down a light-dark pair. Embedded in that rhythm are coarse sand streaks, tsunami run-ups from offshore megathrusts. A grad student counts thousands of layers, matches ash fingerprints from known eruptions, and ties 3 sand streaks to a period when B10 rose and tree rings show short, cool summers. Does that prove the core whispered those waves ashore? No, it proves the decade was busy. Meanwhile, South American lavas from Piranha and African basalts record odd field directions around the same broad intervals that archaeomagnetism in the Middle East shows intensity spikes. The field has a long memory of changing patterns, sometimes with reversed flux patches, like today's South Atlantic dent. When those patches roam, the shield above swings with them. That's the messenger we can read in stone. Now the stakes. If we're entering a decade where intercore lag, reorganizing core flow, and rapid surface mass moves overlap, the closest analogs live in these archives. They say, expect more auroras at odd latitudes, expect satellite headaches, expect climate wiggles that ride on top of human-driven trends, and expect natural hazards to cluster because they often do, independent of the field, when stress chains line up. The record doesn't hand us dates, it hands us posture. Caution belongs here. Proxy records carry biases. Erosion erases layers, lava dates have wiggle, cave drips skip years, human kilns cluster by culture. Correlation can seduce. That's why cross-discipline stacks matter. When B10 in ice, 14C in trees, archaeomagnetism in clay, and satellite-calibrated models all agree on a weaker field interval, trust goes up. When tsunami sands and coral microatolls add clustered geohazards nearby in time, attention goes up. Not because the core commands, but because Earth has busy decades. Impact is practical. Coastal cities move from single hazard plans to compound risk drills. Space agencies time satellite launches for solar minima and beef up shielding if field models say the dent will widen. Grid operators in mid-latitudes treat storms like higher probability hits for a spell. Seismologists don't forecast from proxies, they nudge preparedness windows. A last human moment. In a lava field in Iceland, a geophysicist kneels with a compass over a basalt flow that cooled when Phoenicians sailed. The needle points wrong for today, it points right for then. She smiles, scribbles a direction, and adds one more dot to a map that says the planet's heart has stuttered before, and we listen by learning to read. Human playbook. Monitoring, hardening, and honest uncertainty. If the engine is twitchy and the clutch slips, the smartest move is to watch the gauges and bolt down what rattles. That's the playbook. Instrument the planet, harden what breaks first, and be blunt about what we don't know. Start with monitoring, because you can't steer what you can't see. The backbone is global magnetometer nets, tiny huts and rooftop boxes from Alaska to Zambia, streaming the planet's heartbeat in near real time. Stitch those to ESA's swarm satellites mapping the field in 3D, and you get live contour lines of the shield's strength and mood. Add ground GPS arrays and tilt meters that feel slow, slips, and crustal breathing. Thread in the International Earth Rotation Service length of day residuals. The poles wander, and atmospheric reanalysis to separate winds from deep torque. When those feeds cohere, you've got a dashboard that whispers before it shouts. Deep Earth imaging adds context. Seismic tomography refines the lumps and hollows at the core, mantle boundary, the speed bumps that set the coupling. Normal mode studies track the inner core's anisotropy, and those subtle shape changes scientists just flagged. Lab teams push iron alloys to core pressures to pin conductivity and viscosity, so the model's clutches aren't guesswork. None of that gives us a camera at 2,900 kilometers. Together, it gives us a better silhouette. Action is building constellations that don't flinch. A follow-on to Swarm, more polar orbits, tighter calibration between satellites and ground observatories, and open data pipes, so grid rooms and dispatch centers can subscribe without a PhD. Couple that to all-sky Aurora cameras, rheometers, and ionospheric sounders feeding airline ops in plain language. The rule is simple. If a decision depends on space weather or field strength, the person making it gets to feed love, because the cost of ignorance shows up on your bill and your calendar. Hardening sounds expensive. It's cheaper than failure. For grids, that means transformer cores with better steel, more robust winding insulation, and neutral blocking devices on the lines, most likely to pick up geomagnetically induced currents. Add local current monitors at substations, the ECG leads we used to lack. Write playbooks tied to thresholds. At KPX and dBdty, lower long-distance transfers by Z%. Stock large transformer spares regionally, share them across utilities on binding agreements, and exercise the cranes and permits so a swap doesn't get stuck behind paperwork. For timing, treat GPS as a marvelous but fragile gift. Anchor networks with diverse clocks, rubidium and cesium in racks, GPS disciplined but able to coast. Cross-check time over fiber using precision time protocol, and consider E-Lauren or other terrestrial backups where it pencils out. Make holdover drills a thing. Flip to backup time sources during a sunny Tuesday and see what squeaks before a storm finds it. If you handle money, networks, or safety systems, this is your to-do list today. For aviation, formalize polar route buffers that flex with radiation forecasts and regional field weakness. Keep HF radio proficiency alive, even in the SATCOM world. Equip crews with real-time dose estimates and comms alternatives, and bake space weather checks into dispatch software so the detour decision isn't a midnight debate. Update runway markings and procedures as declination shifts. Buy the paint before you need it. If you fly polar, this is not abstract, it's tomorrow's flight plan. Satellites need both muscle and manners. Radiation-hardened parts where the mission can afford them, aggressive memory scrubbing, watchdog timers, and planned safe mode windows that track the moving South Atlantic footprint. Not last decades. Fly paired orbits for critical climate records so a bad week doesn't erase a season. Budget extra propellant for drag years in this solar cycle. And train ops to treat SAA-ish maps as a sliding geofence, not a fixed square. Coast prepare in layers. Tie seawall upgrades and pump stations to thresholds on tide gauge trends, local subsidence, and those sea level fingerprints, with small deltas for length of day shifts that move tide peaks by minutes. Run compound drills that stack quake, surge, and comms grayouts. Move hospital generators upstairs. Stamp evacuation route arrows where sneakers squeak. Honesty belongs in the same breath as plans. Here's what we know. The inner core's relative slowdown since 2008-2010 is solid. The magnetic field over the South Atlantic is evolving. Day-length residuals breathe on decadal scales. Slow slip modulates hazard on some margins. Here's what's theory. How much of any rotation residual is interior torque versus hydrology? How inner core viscosity changes year to year? Whether multi-year deceleration nudges global M8+ rates at all? We don't have sensors at the boundary. We have models backed by multiple kinds of evidence, and we have error bars. So we act like adults. We build monitoring that's public by default. We set triggers before emotions run the meeting. We budget for resilience where the payoff is clear. And we tell people the quiet part. There's no countdown clock, there's a dashboard. Forecast, 30% chance of aurora, 10% chance of lost YFF, non-zero chance a transformer runs hot. Charge your backup, print the phone tree, and learn which gauge matters to you. One last thing, the timeline you'll want to screenshot is coming up. What to watch in the next 10 years. All right, dashboard time. 10 years isn't geology's usual tempo, but it's enough to tell if this is a phase or a pivot. Here's the watch list that turns deep Earth whispers into decisions you can make on a Tuesday. Start with the planet's clock. Track the length of day residuals from the International Earth Rotation Service. We subtract the known wiggles from winds, tides, and seasons. What's left is the engine's fingerprint. Two things matter. Sign flips. Does the residual swing from net speed up to net slow down? And persistence. Does that trend hold for a few years? Put a sticky note on your calendar for quarterly checks. If the residuals lean into a multi-year slowdown, expect the equatorial bulge and stress bookkeeping to keep nudging. And expect practical knock-ons. More flight detours, tighter timing margins, and busier grid rooms. Next, the pole sprint. The World Magnetic Model updates every 5 years. But mid-cycle corrections are the red flag. Watch how fast the North Magnetic Pole is moving and whether its path kinks. If agencies push an out-of-cycle update again, that's your cue. Compasses, runway numbers, and survey protocols get a refresh. For cities and first responders, that's a real operational change, not a trivia fact. It changes headings, dispatch, and search and rescue accuracy. Now the dent in the shield. ESE's swarm mission posts field intensity maps. Focus on the South Atlantic Anomaly's footprint, area, depth, and whether it's splitting into distinct lobes. Operators already gate instruments for SAA passes. If the contour grows or drifts, those no-go windows expand and creep. Satellite planners should budget for more safe mode time, more shielding, or both. Insurance actuaries will notice first. Satellites tell on the sky. Follow anomaly rates reported by operators and radiation monitors on board. You'll see clusters when solar storms hit, but the baseline matters. If single event upsets and star tracker dropouts tick up outside known storm windows, especially near the SAA's edges, that's a surface-level metric of deeper reorganization. Air and orbit share another dial, drag spikes. Space trackers publish station-keeping burns. When LEO fleets burn more often than models predict for comparable solar inputs, energy is coupling into the upper atmosphere differently. That's a combined effect, space weather and field geometry, yet it's practical. Constellations will age faster, and debris management gets harder. On the ground, magnetometer reach is the everyday tell. Mid-latitude stations lighting up harder and more often during storms means more geomagnetically induced current risk below. Grid operators should tie specific dBay DT thresholds to playbooks, reduce long-distance transfers by X, enable neutral blocking by Y, and then drill them. Watch utilities that publish GIC readings. Copy their thresholds before you need them. Seismic dashboards deserve a slot. We can't predict quakes, but we can set windows. Pair slow slip calendars for places like Cascadia, Hikurangi, Nankai, and Guerrero with the rotation residuals. When slow slip clusters overlap a multi-year slowdown in spring tides, that's a preparedness quarter. Move drills up, check seawall pumps. It's probability math in plain clothes, with your evacuation time and building safety on the line. Sea level fingerprints belong here too. Tide gauge trends that diverge from global mean after you account for subsidence tell you when regional gravity and rotation are tipping the basin. If your local high tides arrive minutes off the old ephemerides, Talk to your harbor master about gate timing, and to your council about crest height before it's a headline. Timing resilience is the quiet hinge. Ask critical facilities, exchanges, data centers, hospitals. 2 questions. Can you hold nanosecond grade time for 24 hours without GPS? And do you have a second independent feed? If the answer is no, put a date on a purchase order for rubidium or cesium, fiber PTP, and E-Lauren where available. Then schedule holdover days twice a year and fix what squeaks. Aviation can pre-commit. Airlines should expand polar route buffers tied to radiation forecasts, not just solar cycle lore, and update crew guidance as the auroral oval wanders. Airports in high latitudes should budget for runway renumbering and navigation chart updates ahead of schedule. If Aurora headlines keep drifting equatorward, expect more HF comms days and plan alternates. Finally, policy triggers. Define thresholds now, not during a storm. Example set. If KP exceeds 7 and mid-latitude D-BAS DT passes X, the grid executes Plan B. If swarm shows the SAA area grows by Y% in a year, satellite programs add Z kilograms of shielding. If length of day residuals stay negative for 8 consecutive quarters, coastal drills align with spring tides and slow slip windows. Add one more. If the world magnetic model pushes a mid-cycle update, emergency services retrain on declination that month, not next year. The paradox here is simple. Tiny numbers on a dashboard decide whether your lights stay on. Personal dials are simpler. If you rely on GPS to work, farmer, surveyor, drone pilot, keep an offline map, a second constellation receiver when possible, and a written checklist for storm days. If you run a small business that needs the internet at a specific time, add a UPS and a basic atomic clock disciplined time source. If you live on a coast, learn your evacuation route and check when your local tide gauge hits its seasonal peaks. If you run ops for anything critical, subscribe to space weather alerts and the IE-ERA's bulletins. Make it a morning habit. The payoff isn't drama, it's fewer bad surprises. If the needles lean together in this decade, we'll know, and we'll have receipts. The planet's heart won't quit, but when its rhythm shifts, everything from compasses to coastlines keeps time with it. If you want the next chapter on where the magnetic shield is heading, subscribe and stick around. Then cue up our deep dive on grid survival. If this clarified a scary topic, share it with one person who needs a calm dashboard, not a countdown clock.